Okay. طيب. So today we'll continue from where we stopped last week. Just a quick recap of what we've learned up till now regarding filters. We studied 2 lectures. Today is our 3rd lecture on filters. We studied the concept of filters, how they work, their frequency response. We studied that there are 4 types of filter, which are low pass, high pass, band pass, and the opposite for that is band stop. Okay, these are the 4 basics. We also studied that there are 2 ways to implement a filter, either passive or active. Active. What is the difference between a passive and an active filter? Do you remember?
Passive, we can use the resistance,
Okay.
capacitance,
Uh-huh.
and inductor.
Correct. And for the active, what do we use?
RC. Operational amps.
Exactly. So for passive filter, we use basic passive components like resistors, capacitors, and inductors. For active, we use them plus an operational amplifier. Now, for the operational amplifier, we have 2 types of circuits, and that's what you were referring to, inverting and non-inverting. Okay? So these are the things we studied until last week. We studied about this. Today, we're going to learn a little bit more advanced circuit types. Remember that when we studied filters in the first week, 2 weeks ago, we said that we have ideal and non-ideal behavior, right? For example, we said that this type of behavior, when this is frequency and this is gain, this is a low pass filter, right? But this is an ideal low pass filter. Realistically, a realistic or non-ideal filter will have, first of all, fluctuating gain. It will not be stable. And second of all, it will have roll-off. It will not directly transition from pass band to stop band immediately with 90 degrees angle, right? It will gradually decrease. And when we looked at our circuits, for example, our passive or active circuits, we noticed that this roll-off is based on the order of the filter, right? When it was first order, we noticed that it is 20 decibels per decade. Every decade, the gain will either drop or increase by 20 decibels. When it is a second order filter, it became 40. When it's a third order, it became 60, and so on. The more you add to the filter, the more that this transition becomes, so this is 20, 40, 60, 80, and you get closer and closer to the ideal sharp transition, right? So today we're going to study how can we design or implement a filter to make it closer to the ideal characteristics. And we're going to do it in reverse engineering. We're also going to look at different types of filter circuits, and I'd like to see these different types in your project, okay? But before we do all that, we want to study what is normalized frequency response, and then we'll go through these. Now, mainly, we said that there is a trade-off. When you want the filter to have a better transition from pass band to stop band, so usually when you want the filter to become a little bit more sharper here, this will result in a little bit fluctuation there. If you want it to be a little bit more steady here, you want it to be stable, no fluctuation, a straight line, it will start to take longer to transit. So it's a trade-off between, do you want minimum fluctuation in gain, or do you want sharper roll-off transition? Clear? And it's a trade-off. If you get this, this will be a little bit messed up. If you get the gain, the roll-off will be longer. If you get a sharp roll-off, the gain will be fluctuating. Clear? Generally, there are 3 widely used filters when it comes to design. So as filter designers, up till now, what have we been doing? I've been showing you a circuit and I will tell me what type of filter it will be. And then we have to find what is the output divided by the input, and then we have to plot the frequency response, and then we decide what the filter is, right? But as designers, this is not how we go. As designers, you have pre-existing designs. And then you select what frequency response do you want? How do you want the filter to behave? And then based on that, you select the value of the resistances and capacitors based on your cutoff frequency, okay? So usually it's the opposite. It's reverse. You don't start with a circuit and then you derive the function. You start with the required function, and then you derive the value of the components that you need to create that, okay? There are generally three widely used pre-existing filters. Today I'm going to go into details about one of them, which is the Butterworth filters. They also are called maximally flat filters, which should tell you which type of trade-off they're choosing. Maximally flat is referring to the fact that their gain will always be flat. Their roll-off depends on their order, okay? The other two types, alternatives that I want you to go and look on your own for them as part of your research for a group project is the Chebyshev and the Bessel filters. All three of them are commonly used filters because of their advanced or their enhanced outcome. Clear? Okay. So Butterworth have maximally flat, which means the gain is almost constant in the pass band. Chebyshev, they have equal ripple, which means there is some ripples, but the difference is they are equal. Rather than something like this, they are equal. So they can be also predictable to someone. And then you have the Bessel filters. So for Chebyshev and Bessel filters, I would advise you to go and look them up online, do some research on them, and then based on what we will learn today and what you will learn from your research, decide which circuit fits the application best. Do not use a simple RC circuit because that will be the least innovative and the least functional one. Okay? Okay. So with that, before we go into this, let's talk about normalized frequency response. Now, as designers, you're all in groups and you all have the same design task, right? How would you decide which circuit is better? If I use, for example, the Bessel filter or the Chebyshev filter, or is it better to use a first order or a second, or how would you judge? Generally, if you want to compare two things, what is the requirement for the comparison to be fair and meaningful?
Easy one.
Easy, okay, makes sense. And
Here one.
shared. Shared. So you need something common, right? You need to have a common base. So if I'm to compare two filter circuits, I cannot compare a high pass filter with a low pass filter. It doesn't make sense, right? But if I want to compare a low pass filter circuit A and low pass filter circuit B, it will not be fair to say, well, for the first one, the cutoff frequency is 100 kilohertz, and for the second one, it's 50 megahertz. These are two different frequencies, right? And we know that components behave differently at different frequencies, right? Which means in order to have a fair comparison, we need what is called the normalized frequency response. Normalized means what? Normalized means standardized, where instead of having multiple cutoff frequencies for your filter circuits that you want to compare, you make them all have the exact same cutoff frequency. How can we do that? If one has 50 kilohertz and one have, let's say, 10 megahertz, you'll take the first one, divided by 10 megahertz, divide its frequency response by 10 megahertz, and take the first one and divide it by the 50 kilohertz. So what essentially you do is you make them both have the same cutoff frequency value, which is 1. If you divide the frequency by its own value, it becomes 1, right? So therefore, we create what is called the normalized frequency response. Normalized means when you start to look at the frequency response, all of your circuits will have the same cutoff frequency of 1. Then you can compare them because now you have a fair base. All of them have the same cutoff frequency. Then now I can compare how they transition between pass band and stop band, how do they have the gain before that cutoff frequency, and so on. Okay, so where do we start? How do we do this normalization? We start with the transfer function. This is the Laplace transfer function of a second order system. All you have to do is take it, divide both the numerator by omega n squared by omega n squared. You've divided by the natural frequency, and therefore you end up with this component, s over omega n, s over omega n. Now remember that s is actually a frequency value, j omega, right? So if you take s and replace it by j omega, this is what you get. And this ratio, omega over omega n, is called the normalized frequency. And the cutoff frequency will always be 1. When you take the frequency and divide it by its natural frequency, the value will be 1. So the cutoff frequency will always be equal to 1. Clear? So this is the first thing. If you want to compare multiple filter circuits, you have to not compare their transfer functions regularly. You have to compare the normalized frequency response. So you have to divide by omega n first. Clear? Okay, That's one thing. Now, why do we normalize? After all of this, why do we normalize? For what? Why do we have to do this? Why do we normalize? Because you've mentioned it, because it's easier. It's convenient. It is a convenient way to standardize, to have a standard, a common base to compare with. Okay? Because otherwise, what will be the alternative? You have two different circuits. One is built in a way, one has omega is equal to 10 kilohertz, one is omega is equal to 50 megahertz. This means you have to go back and change the values of the resistors and of the capacitors just to make sure that they both have the same frequency, right? This is difficult. The easiest way is just divide by a factor so that they will both have the same frequency. Clear? So now with that in mind, from this point onwards, within this lecture, I'm going to explain using normalized frequency response, just to make it easier to compare and contrast, okay? So I've mentioned that I'll teach different ways to implement filters than the ones that we've learned last week and the week before, simpler ones. The first way I want you to think about is the Butterworth low-pass filter. Now, Butterworth filters, don't think of them as circuits, think of them as equations. So in these types of filters, we'll do the reverse engineering. Last week, what did you do? I used to give you a circuit diagram, and then you had to calculate V out divided by V in, and then from that you had to plot the transfer to calculate the transfer function, and then plot frequency response, right? However, when you want to design a Butterworth low-pass filter, it's slightly different. What you do is, because you're coming in as a designer, right? So you already have a design requirements, right? You're told current frequency should be equal to this, gain should be equal to that, the transition should be this fast or this slow, right? So what you do is you start with the graph. You start with what type of curve do I look at? What type of frequency response do I want? And then based on the frequency response, there is a pre-existing set of transfer functions which follow this format. Butterworth filter transfer function is always equal to a constant divided by a polynomial. This polynomial could be either first order, second order, third order, fourth order, and onwards. It doesn't stop at 4. I just took until 4 as an example. So basically, what does this mean? This means that a normalized Butterworth first order filter will always have V out over V in equal to A0 over this value, S plus 1. A second order filter will always have a transfer function of A0 over S squared plus square root 2 plus 1. A third order filter will be what? From here. A0 divided by S plus 1 times S squared plus S plus 1. And a fourth order filter will be A0 divided by this equation. So what you have is you start with the transfer function, with the frequency response. And then you decide that, well, I'm not very concerned with the transition. I just want it to be flat. So I'm going to go for first order. Okay, then design a filter that has this first order equation. I want it to be second, third. So you choose the shape. And then from the shape, you already have a pre-existing formulas for output divided by input. And then for each of these formulas, there are different circuits that will give you the exact same formula. So you don't start with the circuit, then the formula, then the frequency response. We start with frequency response. What is the formula that achieves it? And then we have pre-existing, think of it as the circuit exists. You don't have to design the circuit. You don't have to come up with, how am I going to connect a series or parallel? You don't have to worry about that. It's there. All you have to do is select values of its component that will give you the requirement. Make sense? So the circuit is there. So now I'm going to give you examples of these circuits. But before we go, do you notice something about this transfer function or this frequency response? Regardless of the order, if it's first or 10th, what do we notice? We said there are two things that makes the filter ideal. How fast it transitions or how sharp it transitions from pass band to stop band, and how steady the gain is. So what do you notice about the Butterworth filters? If you look here at the pass band, so this is pass band, and this is stop band, right? And this is the cutoff frequency. In the passband, what do we notice?
Zero.
The gain is flat, right? 0 decibels mean 1. That's normalized frequency response. So the gain is 1, the cutoff frequency is 1. Do you notice? The gain is 1 because 0 decibels mean 1, and the cutoff frequency is? This is normalized. So we can compare the first and 10th order. So we have to go normal. But you notice the gain is flat. There is no ripple. It doesn't go up and down and fluctuates. It's flat. So this is one of the benefits and why Butterworth is one of the commonly used filters. Yeah. But if I wanted to get a sharper transition, then with increasing order, we are getting closer to the ideal, right? And if you compare this curve, which is first order, to this curve, which is 10th order, you'll notice that first order is a little bit slower in transition. And then second order, the transition is a little sharper. And then when you jump to fourth order, it becomes sharper. And then when you get to 10th order, so the more the order is, the sharper the transition is from passband to stopband. Does that make sense? So this is the Butterworth filter. Now, we already know the frequency response. We already know the equation. Now I'm going to show you examples of circuits that you can use, okay? So let's start with this one. This circuit is actually a Butterworth low-pass filter that is second order. And by the way, Butterworth filter can be for second, third, any type of order. There are circuits that are Butterworth, okay? For example, this circuit over here. This doesn't look like the simple RC circuit that we studied last week, right? It's like, but what does it offer? It offers stability because it's a Butterworth filter. So the gain will be stable and flat. And just to confirm that this is in fact a filter circuit, all you have to do is just calculate the transfer function. V2 over V1. So if you look here, the circuit can be restructured. It is equivalent to what? A resistor, Rn, an inductor, Ln, and then Rn and Cn can be considered a parallel branch. Let's call it ZC parallel with R. Here we have the input V1, and the output is the voltage across the parallel branch V2, right? Now, can I find the transfer function H of S, which is V2 over V1? So I can use voltage divider rule, right? Which states that the voltage V2 over V1 will be equal to the parallel branch impedance divided by the total impedance, correct? Let's start, so let's call this equation 1, just for reference. Now let's try to find what is ZC parallel with R. What would that be equal to? How do we calculate parallel impedance? Do you remember 1 over ZP is equal to 1 over Z1 plus 1 over Z2, right? Which means that ZP is equal to Z1 times Z2 divided by Z1 plus Z2. Do you remember these rules? It's the same rules of resistive networks. نفس قواعد الدوائر الكهربائية العادية اللي في المقاومات فقط. فضربهم على جمعهم, right? So for this parallel branch, it will be ZC, which is 1 over SC, multiplied by ZR, which is R, divided by 1 over SC plus R. Here. And then I will simplify just to make it easier for me to calculate. R multiplied by 1 over SC is R over SC. And for the denominator, we can unify it. اللي هو نوحد المقامات في المقام. المقام المشترك هيكون S C. And here we'll have 1 plus SCR. Just a moment. Okay. So what happens then? This C and this C counter each other out, and what we have left is R divided by 1 plus SC. This is ZC parallel to R, right? Okay, now let's calculate the total. What is the total impedance of all of them? Are they connected in series or parallel? Let's look here.
Here.
Series. And the series total impedance is what? What do we do?
This.
Add them. Plus, exactly, plus. So it will be what? R plus L, ZL plus L parallel branch Z, parallel R, right? Which is equal to what? R plus SL plus R divided by 1 plus SCR, right? To simplify it, the total I'm gonna combine them as a single fraction. يعني بدل ما يكون 3 حدود R و SL و fraction هجمعهم ككسر واحد بتوحيد المقامات. The common fraction will be with the denominator of 1 plus SCR. We'll take this R, multiply it here, right? R times 1 is 1. R times SCR is SCR squared, right? Plus, then I'll take SL and multiply it here again. SL times 1 is SL. SL times SCR is S squared LCR, right? Finally, plus R. So far we good? Let me just organize it by order. So it will be S squared LCR plus, so I'm just ordering it by the power of S, and of the S squared S, and then without S. This is S squared. And I have two terms with S. I have SL and SCR, right? So I'll take S as a common factor. S times L plus CR squared, right? What do I have left finally? What's the last thing left? R. How many R's do we have? R and R, right? So 2R, okay? 1 plus SCR. This is Z total, صح? Let's call this here 2, and let's call this 3. Can I substitute 2 and 3 in 1? Remember, we're looking to find V2 over V1. So what I will do next is substitute 2 and 3 in 1. So V2 over V1 is equal to the parallel branch, which is R divided by 1 plus SCR, صح? Divided by Z total, which is S squared LCR plus S times L plus CR squared plus 2R, all divided by 1 plus SCR, right? These two cancel each other out, correct? And what do I have left? R divided by S squared LCR plus S L plus CR squared plus 2R. So I have values of R, of L, of C. Can I substitute them? Let's substitute the actual component values. So we can say transfer function becomes R is what? Can we see the value of R? From the R is what? 1 divided by S squared times L is what? Here, square root 2. And C is, so square root 2 times square root 2 is square root 2 times square root 2 is equal to 2, right? So 2S squared plus S times L is what? And so square root 2 plus C is what? Square root 2. R is what? Square root 2 times 1 squared, which is equal to what? 2 square root 2, and square root 2 plus square root 2, right? So 2 square root 2. 2 square root 2, just enhance. Just deleted the entire thing. We'll start again, it's okay. So we said we want to substitute. So h is equal to r divided by 1 plus SCR, which is equal, divided by, so the total, which is S squared LCR plus L plus CR squared times S plus 2R divided by 1 plus SC. These two counter each other out, and what we have left is R divided by LCR times S squared plus L plus CR squared times S plus 2R. Said R is equal to 1 divided by L times C times R is 2 S squared plus L is square root 2. CR squared is square root 2. So square root 2 plus square root 2 is equal to 2 times square root 2, right? So 2 times square root 2s plus 2r is equal to r. R is 1, so 2r is 2. 2. So can I take 2 as a common factor? So it becomes half, right? 1 over 2. So half is 0.5 divided by s squared plus square root 2s plus 2, right? This is our transfer function. Based on these values in the circuit combination, right? Now, if you look at this transfer function carefully, half divided by s squared plus square root 2s plus 2. Does it look like something from the table? Which is this one, right? Which is a second order filter, right? So this circuit is in fact a second order low pass filter. And therefore, even without plotting, we know that this curve represents the normalized frequency response for it, right? So knowing that, if you know the transfer function, you can find the circuit that will fit this transfer function, makes your work as a designer a whole lot easier, right? So let's keep that in mind. Now, so this here is a passive second order low pass filter which satisfies Butterworth design. This circuit over here is called the Salem key section, this type of circuit. This Salem key section is an active first order low pass filter. Okay, now we've studied this last week. Do you remember? We said that this here is a passive low pass filter, and this here is a non-inverting amplifier circuit. And the total gain V out over Vn is basically the gain of the amplifier multiplied by the gain of the filter, right? So here, the gain of the filter is 1 over 1 plus SCR multiplied by the gain of the non-inverting amplifier is 1 plus R2 over R1. Do you remember this from last week? Yeah? Okay. So if you look at this, we can say that the gain H is equal to 1 plus R2 over R1 is an entire constant value because the resistant value is constant, right? It doesn't change with change of frequency. So you can say 1 plus R2 over R1 all divided by 1 plus SCR. This is your transfer function, correct? Now, if you compare this to, what do I have? To my table, what does it look like? It looks like this normalized frequency, right? It's a constant divided by S plus 1, right? And if you look here, this is the normalized frequency, S divided by 1 over CR, right? So this filter, the sailing key section, is also a Butterworth filter, but it is first order, right? Because the power of S is 1, which means that the transfer function or the frequency response will always look like this curve over here. Clear? So the circuit exists, the transfer function for it exists. All you have to do as a designer is do what? Select what are the values of R and C that you want and component values to give you the frequencies that you need. Make sense? Clear? Okay. Let's give you another example. This here is a second order low pass filter. This is a sailing, so this one was a first order sailing key section. This is a second order sailing key section. This here, now I don't want you to go through the derivation of V out over Vn. Just keep in mind that if you use circuit analysis theorem, this will be the transfer function that you're looking at, okay? If you analyze this circuit and try to find what is V out over Vn, this is what you'll end up with. Clear? Keeping that in mind, do we remember we studied something called a standardized second order equation? The formula for standard. We studied that when we were trying to analyze systems and we wanted to find damping ratios and cutoff frequencies and so on. So that was in lecture 5. If you don't remember it, you can go back and check for it. But for now, this is a standard transfer function for a second order circuit. Okay? Keep that in mind. So this is the standard. What does that mean when I say the standard transfer function? It means any second order circuit has a transfer function that is in this format, in this general form. Okay? And usually we take this form to compare the transfer function of a circuit so that we can find out what is the value of A, what is the value of zeta, what is the natural frequency, and so on. Clear? So this is the standard form, and this is the actual transfer function that we've calculated or that we've derived from circuit analysis methods. So what you'll do is if you compare the standard form to the actual circuit, you can get values that are important to you, okay? For example, you can compare this to this and you can find the value of gain, right? A0 represents gain. What is gain is equal to by comparison? بالمقارنة يعني المعادلة اللي على اليسار هي الستاندرد فورم. المعادلة اللي على اليمين هي ترانسفير فانكشن المحسوبة من الدائرة. فلو قارنت معادلة الدائرة بالستاندرد فورم هتوجد قيمة A0 اللي هي الجين، قيمة أوميجا N اللي هي الناتشورال فريكونسي التردد اللي الدائرة هتشتغل عليه هو ناتشورالي، والزيتا اللي هي الدامبينج ريشيو اللي هو if you remember we discussed damping ratio which told us will the circuit fluctuate and then stabilize? Will the circuit slowly stabilize? Will the circuit immediately stabilize? All of this depends on zeta. We studied that before. So A, zeta, and omega n are performance metrics. Do you remember when we studied performance metrics? Rise time, fall time, settling time, and so on, right? So if you compare the standard form to the circuit transfer function that you have, you can get the values of these performance metrics. Yes? واضحة الفكرة؟ طيب, can we compare left hand side, left hand equation with right hand equation to get A0? A0 here exists only in the numerator, صح؟ فقط في البسط. فبمقارنة بما إنه اليمين إحنا بنفترض إنه بتساوي المعادلتين equivalent صح؟ إذا البسط المفروض يساوي البسط صح؟ إذا A0 هتساوي كم؟ Should be equal to this, right? These two should be equal. Do you agree with that? So therefore, R1 plus R2 over R1. Agreed? طيب. Can we compare the first term in the denominator with the first term in the denominator? They have to be equal, صح? Which means that 1 over omega n should be equal to RC, which means omega n is equal to 1 over RC. Agreed? Finally, can I compare middle term here, the middle term here? Possible? All the way up to here. Well, last term واحد واحد ما Middle term has to be equal to the middle term, right? So let's compare them. We have 2 zeta over omega n. ده معامل الاس هنا صح؟ معامل اس في الطرف الأيمن ايه؟ 3 minus R2 plus R1 over R1 multiplied by RC صح؟ طيب. What does this look like? This one. ايش بقى ده؟ من الأشياء اللي حسبناها already. A0 صح؟ This is A0 والأوميجا n عبارة عن ايه؟ 1 over RC يعني ممكن ناخد الأوميجا n دي ونبدلها بواحد على RC واحد على واحد على RC يبقى ضرب في RC صح؟ These two counter each other out صح؟ And what do you have left? Zeta is equal to 3 minus A0 over 2 صح؟ فإذا بالمقارنة قدرنا نحسب قيمة الزيتا وقيمة الأوميجا n وقيمة الجين. Make sense? طيب. So let's keep these three equations in mind. And remember these three equations are only applicable to this type of circuit diagram, right? نتذكر إنه في الدائرة دي في السالين and key section, second order section, gain, frequency, and damping ratio all have equations that can link them to the component values. Clear? With that in mind, let's try and solve a problem. This is a design problem. It says what? Design a Butterworth low-pass filter with a cutoff frequency of 1 kilohertz and a roll-off rate of 80 decibels per decade. Considering that the numerical values of R1 is 10 kilo ohm and of C is 10 power minus 7. What does that mean? It means صمم دائرة باعتبار إنه عندك على الأقل نوعين من ال components معطاة. You don't get to design them. You don't get to calculate for them. It's a given value. Clear? So let's now discuss the known information and the requirement. Requirement is it has to be Butterworth. Okay? It has to be low pass filter. What is the cutoff frequency value? كم قيمة ال cutoff frequency? From the question? 1 kilohertz. طيب, let's write this. Number 1, FC is equal to 1 kilohertz. صح? Usually we don't deal with frequency in hertz. We deal with frequency in omega, right? In radian per second. So you have to convert from F to omega. So omega C will be equal to 2 pi FC, right? So omega C is 2 pi FC اللي هي 2 pi times 1 kilo 10 power 3 صح؟ 10 power 3 radians per second. Let's keep that in mind as we convert it from hertz to radians. طيب. Roll off is 80 decibel. What does that mean? Roll off is 80 decibel. Roll off is the transition from pass band to stop band. Roll off, if we go back to this figure, if this here is your pass band, this here is your stop band. This, for example, this range is your roll-off, okay? If you remember from the last couple of weeks, we studied that for a first order circuit, the roll-off is 20 decibel per decade. بمعنى, when you plot this omega versus gain, you start with stable gain, right? If it's first order, you start to drop. The rate of the drop or the slope of the line ميلان الخطة معتمد على الأوردر. If it's first order, the slope will be 20 decibel per decade. Means every 10th, يعني when you're going from 10 to 100, you drop 20 decibel. From 100 to 1000, you drop another 20 decibel, and so on. If it's second order, the drop becomes 40. If it's third order, the drop becomes 60. So with each order increment, the slope or the roll-off at 20. So here you're told that the roll-off should be what? 80 decibels. So that means what order do we have? What type of order are we working with? Fourth order. 80 decibels. So this is a way of telling you that it's fourth order without clearly telling you it's fourth order. It's giving you an information that you have to interpret. تفسر المعلومة على إنه this means it's fourth order, right? So what I want here is a fourth order filter. خلاص, I need a low pass filter. I need it to be a Butterworth filter. I need it to be fourth order, right? Okay, I know what fourth order filter have transfer function of. We already know that any Butterworth, where is it? Fourth order filter will have this transfer function, right? It's A0 divided by this value, right? So from that, let's take this information. Where's the question? Okay, just keep this information in mind that I have this fourth order, right? طيب, how do you build? Until now, I showed you how to build first order. I showed you how to build second order, right? From these, how can I build fourth order filter circuit? Now remember, on lecture 1 of filters, I said, if you want to build a higher order filter, there are simpler ways and there are more complicated ways. One of the simplest ways, I said, if you want to build a second order filter, you will take 2 first order filters and connect them in series. If you do that, you end up with a second order filter. So if I want to build a fourth order filter, what would I do? If you want to create a fourth order filter, what you can do is take 2 second order filter circuits and then connect them in series. So what you'll end up with is, this will be a fourth order filter. Make sense? So now let's keep that in mind. I know that this over here is the transfer function of a fourth order filter, that is Butterworth, okay? This over here is the standard equation of a second order circuit, right? What I will do is I will take 2 second order circuits, connect them in series so that I will end up with this first order, fourth order circuit, clear? Which is what we have here, okay? This one is second order and this one is second order. This is the circuit that we just studied, right? The question is design. What does the word design mean here? It doesn't mean go and figure out how to connect resistors and capacitors in different ways to get to this result. Basically means calculate component values that will give me the required or the desired cutoff frequency. Here. So what I will do is I'm going to treat them as 2 separate structures. I have my first stage of second order. I have my second stage of second order. And I'm going to break it down that this here belongs to the first stage and the second part of the denominator belongs to the second stage. Here, as if I had 2 separate values that when multiplied together, they gave me this new value. Clear? And then for each stage, I'm going to use the exact same rule that we've just derived. Are we following? So these rules, A, omega n, and zeta, these are the exact same rules we derived here. This is A, this is omega n, this is zeta. And I'm going to apply the exact same rules to each one of the 2 stages. Clear? Are we following? Okay, so this is what we'll have. So I'm going to start with the first stage, and I'm going to compare it to the denominator of a second order, standard second order Butterworth filter. If you compare this to this, what do you find? We can find the value of zeta, right? So step 1 is easy. Compare middle term here to middle term here and find the value of zeta. Zeta 0.765 is equal to 2 zeta. Therefore, zeta is equal to 0.765 5 divided by 2, which is equal to 0.38 something. Okay, clear? Now let us compare this zeta here, or let's implement this zeta value here. 2. I know zeta. Can I find the value of A using equation 2? Sure, right? Because if you know zeta, the only unknown remainder is A. So we can say that in this case, A will be equal to what? A0. And let's call it A01, and let's call this zeta 1 because we're treating the first stage. So this is 2 times zeta 1. 3 minus this. So 3 minus 2 plus zeta times zeta 1, right? Which is equal to 3 minus 2 times 3.8, which is 0.765. So A01 is equal to what? 2 point what? 2.3, almost, right? Approximately. So we have zeta, we have A0, and then if you know A0, and from the question, we're given what? R1 value and C value. R1 is 10 kilo ohms, C is 10 power minus 7. Let me write them down. R1 is 10 kilo ohm, and C is 10 minus 7 farads. Okay, so we know Z1, we know A1. Can I find the value of R2 using this formula over here? If you know R1 and you know A0, you can find R2, right? So we can say that R2 is equal to okay, R2 will be equal to what? A0 times R1 minus R1, right? From this formula over here, which is equal to A0, which we just calculated to be 2.23, times R1, which is 10 power 4. 10 kilo means 10 times 10 power 3, which is 10 power 4, minus 10 power 4, which is equal to 1.23 times 10 power 4. So this is R2. Clear? Make sense? This line I'm confused. How are you feeling? Should I start from the beginning? شوف يعني احنا اوكي عشان ما تحسوا بالضياع. في فكرتين للتصميم كديزاين انجينيرز، انك يا اما انك الديزاين تبداه من البدايه انه كيف حوصل الدائره بحيث انه الانبوت والاوتبوت يكون علاقتهم كذا، انه اختار مش بس قيم، اختار طريقه التوصيل نفسها انه يكون توازي توالي، كم كومبوننت، كيف حيتوصلوا. This is a way. This is not we need here. There is another way انه يكون already عندك الستراكشر موجوده، فقط المطلوب منك حساب القيم الداخليه اللي حتطلع القيمه المطلوبه للكت اوف فريكونسي. اوكي، طيب في الحالة اللي احنا بنستخدم حاجة اسمها الباتر وورث فلتر، اللي هي ريفيرس انجينيرنج، هندسة عكسية. بدل ما نحن نبدأ من الصفر من نقطة A لنقطة B، بنبدأ من B عشان نختار A اللي حتوصلنا. وضحت الفكرة؟ يعني as if أنا I know where I want to reach, so I'm going to design for that specifically. حلو؟ فاحنا بادئين انه احنا عايزين نعمل ديزاين. السؤال انه ديزاين باتر وورث فلتر، وبالتالي انا عندي اوريدي المعادلات الترانسفير فانكشنز المطلوبة للباتر وورث فلتر. عندك معلومة انه الرول اوف 80 ديسيبل. 80 ديسيبل معناها فورث اوردر، صح؟ فبكل بساطة برجع للباتر وورث فلتر ترانسفير فانكشنز المعادلات واشوف اي معادلة هي للفورث اوردر فلتر. طيب اللي هي المعادلة دي بالمقام البسط حيكون ثابت A0. حلو؟ طيب الفلتر الفورث اوردر هو عبارة عن تو فلتر سكند اوردر، صح؟ طيب انا عايزة اصمم فورث اوردر، لكن ما عندي دائرة جاهزة الفورث اوردر، لكن عندي دائرة جاهزة السكند اوردر، صح؟ اللي هي الدائرة اللي اخذناها سيلين كي سكند اوردر سيركت هنا، صح؟ طيب الدائرة دي لما اخذت قارنتها ال V out over V in بتحليل الدوائر اللي هو المعادلة تحت دي بالستاندرد فورم، المعادلة الثابتة لكل second order system، ممكن بالمقارنة أوجد قيم ال A نوت والأوميجا نوت والزيتا، صح؟ فإذا أنا عندي معلومتين مساعدين، إنه أنا عندي دائرة من second order، ومن الدائرة دي عندي مقارنات تحسب لي إنه أنا لو عايز أحسب لجين معين أو لكت اوف فريكونسي معين كان المفروض تكون قيم الآر والسي والآر 2 والآر 1، صح؟ اللي هي المعادلات دي اللي هم الثلاثة اللي استنتجناهم دول. أوكي؟ في نفس الوقت عارفة إنه الفورث أوردر عنده معادلة معينة، صح؟ طيب أنا حجمع المعلومتين دول وأبدأ أقارن، إنه حأعمل أقول أوكي فورث أوردر معناها 2 سكند أوردر موصلين مع بعض، وكل سكند أوردر على حدة عندها قوانين تابعة للسكند أوردر أناليسيز اللي أنا عملته. في نفس الوقت ممكن أقارن إنه أعتبر إنه الفورث أوردر الجديدة دي اللي هي عبارة عن A0 على S تربيع زائد 0.765S زائد 1 ضرب S تربيع زائد 1.848S زائد 1، أعتبر إنه المعادلة دي في الأصل كانت معادلتين ضربناهم في بعض، A01 على S تربيع زائد S زيتا S زائد 1 ضرب A02 على S تربيع زائد 2 زيتا 2S زائد 1. حلو؟ فلما ضربنا الاثنين دول طلعنا ب A0 اللي هي عبارة عن A01 ضرب A02 والمعادلتين دول الأولى والثانية، صح؟ إذا زيتا 1 بتساوي زيتا دي وزيتا 2 بتساوي زيتا دي، صح؟ اللي هنا أوكي؟ طيب وانس أنت عندك قيمة الزيتا ممكن بعد كده تعوض في القوانين دي تحسب قيم ال R1 وال R2 وال C وال R والأشياء المتبقية. اتضحت الصورة؟ أوكي؟ فبدينا بالتعويض المباشر، حسبنا قيمة زيتا 1 من الجزء الأول النصف الأول من المعادلة، وبناء عليه حسبنا قيمة الجين، وبناء على الجين قدرنا نحسب قيمة R2. إلى هنا واضح؟ أوكي؟ طيب الجزء الثاني نحسب قيمة، لو رجعنا هنا احنا عندنا معطيات، قلنا عندنا R1 وعندنا C، صح؟ لما نقول لك ديزاين يعني احنا شرحنا ان الكونسبت ديزاين معناه اوجد قيم العناصر المكونة للدائرة، صح؟ فالR1 موجودة والC موجودة، المتبقي ايه الغير موجود؟ R، صح؟ قيمة الR ما عندنا، والR2 في الدائرة الأولى والR22 في الدائرة الثانية، صح؟ طيب احنا من حسابنا هنا وصلنا للR2، صح؟ ايه الباقي؟ الR، صح؟ طيب هل في معادلة هنا بتساعدنا على الحصول على الR؟ هنا عندنا C معطى، صح؟ من السؤال قال انه افترض انه عندك قيمة لسي اللي هي 10 سالب 7، وعندنا قيمة الأوميجا إن. أوميجا إن هي إيه؟ أوميجا إن الناتشورال فريكونسي أو الكت اوف فريكونسي، صح؟ إحنا عندنا في القانون أو في المعطيات إنه عايزين الكت اوف فريكونسي يكون بقيمة كم؟ 1 كيلو هرتز، وإحنا حسبناها قلنا 1 كيلو هرتز كم بالأوميجا، ممكن نحسبها عادي، صح؟ طيب إذا أوميجا إن بتساوي 2 باي اف سي، صح؟ هي بتساوي 2 باي في 1 كيلو اللي هي الكيلو 10 أس 3. وبتطبيق القانون ده ممكن نقول إنه الR بتساوي 1 على أوميجا إن سي، صح؟ إذا الR بتساوي 1 على 2 باي في 10 أس 3 في 10 أس سالب 7. أوكي، واضحة الفكرة؟ إذا كم قيمة الR بتكون؟ كم؟ 10 باي يعني 1 over 2 باي multiply 10 power minus what؟ 4، صحيح. بعد كده ممكن نحسبها ونوجد قيمة الR. اتضحت الصورة؟ طيب كده حسبنا الR، خلاص الR بقت موجودة ليهم كلهم لأن الR ثابتة، وحسبنا هنا الR21، صح؟ باقي إيه آخر شيء؟ R22. طب R22 هنحسبها كيف؟ هناخد الجزء الثاني من معادلة الفورث أوردر ونقارنه بمعادلة السكند أوردر، صح؟ which is what we have here. هناخد السكند بارت ده ونقارنه بدي. من هنا هنطلع أول شيء بالزيتا، صح؟ this is step 1. get zeta. Step 2, get A0. Step 3, get R2 from A0. صح؟ الأوميجا we already calculated. We don't have to calculate again. طيب zeta is equal to what? zeta 2 بالمقارنة 1848 divided by 2 صح؟ which we can calculate later on. طيب step 2 from zeta get A0. A02 is equal to 2, 3 minus 2 zeta, which is 3 minus 1.848, right? Which is equal to what? 1.16 something تقريبا صح؟ or 1.15. If we know A0, can we find R2? Yeah, R22. R, let's do it here. R22 is equal to A0 times R1 minus R1, right? 1.15 تقريبا approximately times R1 اللي هي 10 kilo ohm, so 10 power 4 minus 10 power 4, right? Which is equal to 1.15, 0.15 times 10 power 4, right? Okay? 10 power 5 as a common factor, 1.15 minus 1 times 10 power 4, صح? Okay? So now we know R22. So we have effectively calculated all the component values that we need to build this design, given the information that we have. Clear? أي سؤال إلى هنا؟ طيب what if we were told to design a 6th order filter? What would you do? You'll just add a third one here, right? Then you'll go and look what is the equation for the 6th order Butterworth filter. تشوف المقام بتاعه وبعد كده هتقارنهم. طلعت الفكرة؟ Clear so far? These are nicely written ones because I know my handwriting is not the easiest to follow, but it gives you the exact same results that we had earlier, okay? So generally, now let's remember or recap. Using Butterworth filters, Butterworth is type of filter that can help you instead of going from circuit to design the circuit itself. All you have to do is decide what type of frequency response you're looking at. فإحنا بنعمل reverse engineering. بدل ما نبدأ بتصميم الدائرة نبدأ إحنا أي نوع من الترانسفير فانكشن إحنا محتاجين. مثلا في applications that we don't care about the sharp transition but we want the steady gain. I could take a first or second order filters based on the components that I have. Once you decide what transfer function you want or what frequency response you want, you go back here and choose which equation fits that order. And then you go to the pre-existing circuit diagrams using this equation and then compare it to get the value of the resistors and capacitors and components that you have. Clear? Any question up till this point? Okay. So finally, just to give you a summary, if you know how to build a Butterworth low-pass filter and a Butterworth high-pass filter, you can easily cascade them to get a Butterworth band-pass filter. Okay? لأنه intersection point between the high pass and the low pass, which is this overlap, will be your band, the pass band, right? If you want to use them to build a band stop filter, you have to add them parallelly, given that the cutoff frequency for the low pass is lower than the cutoff frequency of the high pass, because that difference is your stop band. Otherwise, it will be just a full pass filter. Make sense? Any questions so far? Okay, I've put here some links just to give you a start in how you can do research to find different circuit types, different circuit diagrams that you can use for your project. And you don't have to just use these, use any resources that you can find online just to look up different circuit. Please do not use the simple two-component circuit. not just the capacitor and resistor. These are just to give you an understanding of the concept, but a lot of the marks are based on innovation, fitness to use. So if you use the regular filters, remember you have to design 6 of them, right? So if this is your filter 1, and it has a large roll-off, because let's be honest, RC circuit or filters, they're first order, right? So they do have the most gradual roll-off, 20 decibels per decade. And then you'll design a second one, which will also have a high roll-off. This is overlapping, which means 2 LEDs will be lighting up at the same time, which is not what you're looking for, right? So try to design filters that will minimize this overlap, that will enhance the performance, but at the same time, you don't want to over-engineer it. You don't want to use so much components that will consume so much energy. You just want it to be clearly visible, the difference between each LED, right? So make informed decisions, slightly deviate from the basic standard filters. Try to find something that is better and more advanced and more innovative, okay? Doesn't mean you have to come up with something on your own and come up with a new design. Just look at the existing designs and which one will work better for you, okay? Any questions? For those who are online, thank you for joining. For those who are in class, I'm gonna ask you to please write your attendance IDs, and then you can go to BG7. Mr. Basim will be waiting for you there for your second practical. Okay? Yes.
It was online,
Okay.
but I think Mr. Basim didn't attend.